is not. So basically, and also the absence of the pedestrian rules of the road. So if we want to stay the pedestrian on the road, basically compared to the cars and cyclists, usually pedestrian, usually they have more different degree of the freedom to move, and it makes add more actually uncertainty in the pedestrian motion. And the other problem is that the pedestrian basically interaction with the environment and the other pedestrian and the cars. For example, you see that it's here how it's crowded at intersections basically, and basically in, for example, Cambridge, and that's a problem. And of course, the other thing, as I said, is basically that when we have the combination of the pedestrian and the cars and the environment, is make it more challenging. And our idea is basically make it this transferable and basically make it this possibility that if you learn in one domain and one city, how we can transfer this knowledge to another city, and the car in different city can use the knowledge that you did and got from different environments and just extend it to the new environment. And the idea is that actually we want to incorporate the transferable features. So if we pick the features and learn that features that is transferable across different domain, which is actually here we focus on the intersection specifically, which is one of the very critical domain, and a lot of accidents happen in this domain because of the complexity. Our goal is to actually algorithm to be transferable, and we can learn the motion behavior of the pedestrian there. And the whole idea is basically based on the context-aware motion prediction. So we don't look at just the pedestrian itself, the trajectories. We look at other, domain and other in the environment aspect of that, some environment aspect, or we call it context. So for example, how, pedestrian far from the curbside, right? What's about the traffic lights status, both the pedestrian traffic status or the traffic lights for the cars. So that's actually, it can play a role in pedestrian behavior and intention. And for example, if it's red, most likely pedestrian stops. Again, all the uncertainty around. But the whole idea is that consider this context in the environment and in context from the environment in the pedestrian motion behavior. And our idea is basically we use some spatial or geometric characteristic of the intersection to be kind of invariant, and be invariant from that. So basically, when you look at this picture on the right side, you see basically the intent of the pedestrian. This two intersection I1 and I2 is basically the same. They try both this, and this trajectory, one of them red on the for I1, the pedestrian tries to turn left, right? The intention is turning left, and the same intention happens in intersection I2. So both of them, they actually imply the same intent. But the trajectory completely is different. So if you, for example, have model that it learns the trajectory in the shape of the one on the left side on the I1, it may not be generalizable or transferable to the new domain with different intersection with different geometry. And the idea that we actually did is basically how we can basically map and find the higher feature, basically that represents that behavior, this intention in similarly. So you see that based on this transformation that we did, basically, based on some geometric and some feature that we extract using some geometric feature of the environment, basically we were able to map two trajectories the same shape, and basically we learned this feature instead. This actually leads to the next part of our algorithm, basically how we can use this model for doing basically transferability in the continual learning. So the idea is basically for the pedestrian and motion prediction and many other prediction is limited to the offline learning. What does it mean offline learning? It means that you have already the data sets and you just use that data set offline and learn your model on it. But our contribution was to do the incremental learning, basically, and then how we can do is basically we are not limited to just our data set that we collected. We improve our model as we go and as we experience new data and as we collect more data sets. So, and we use techniques, we call it actually dictionary learning. I will show in the example. And then basically we find some similarity with what we learned before with what we learn now. So let's show in the picture to make it more clear. So here assume that we have the data at intersections and basically at time t0. And then you have the transferable model that we talked about it in the previous slide. So we learn this behavior. So the blue trajectories are the pedestrian trajectory, and this is the intersection. So they are crossing the intersection basically. And then we use our model. Basically, the second step is actually sorry for that. Second step is actually we learn this model, which is the model M. So we train on the basically this model, and then we train the some trajectory or some dictionary here, some component or motion primitives, and some transition between. And the next time actually we learn a new data set, a new intersection, completely different geometry in time t1. And now we have a new basically model, and this model basically we have a new set of the motion primitives with different colors, red, blue, and green, and basically some transition. For example, from one motion primitive we move and transit to another motion primitives. And now we compare this model. Instead of using, again, training the model, we just train model on the new data set at time t1. So we already have the model M. And when we do the fusion, we actually use the graph representation of this model and then compare it and fuse it. And we use some similarity metrics or measure some similarity metrics based on the cosine distance. I don't go to the detail, but the whole idea is that you find some similarity between these motion primitives and their transitions, and then you can fuse it. So if your model is similar and compared to the previous one, you fuse that model, that part of the graph. Otherwise, you add the new nodes or edges in the graph. And in the first graph actually showing that this dots is a kind of this nodes, basically your motion primitives, M1, and 6, and the edges actually just your transition, basically your transition, basically that from one motion primitives, for example, T1, it shows that the on the top, the motion primitives from 2, it's moved to and transit to motion primitive 3. So it shows that, and it implies the for example, turning left or turning up, basically. So, and we can just continue. For example, we go to a new intersection C, and basically you can collect the data and you can just continually learn the model. So actually we did this, we collected a lot of data sets with 6 cameras and tripod 3D LiDAR at 8 intersection and in Cambridge. And then also we use the golf cart that we have with the 2D LiDAR and the 3 cameras. And we collect all this data, and using this data for collecting the pedestrian behavior. And this is a result that it shows in 5 intersections that we collected. And you see that this is on the left side. This is the error that shows that actually how good our algorithm. Our algorithm shows that the prediction error accuracy, actually opposite of it, is decreasing as we see the new intersection. So not only our model is transferable to different domain, different intersection with different geometry, also the accuracy is improved, or the error is decreased. And also we show on the right side how our model is comparable with the other model, and also actually is outperform the other models. So ours is blue compared to the yellow dash, which is the ground truth, and the other previous model, which is basically the batch model, which means that offline learning, no transfer learning. Even our algorithm shows that it's even better because it sees more variety in the data sets, and it's improved and it's more generalizable. So the model is it outperforms the previous model that is shown. So the next topic that I want to talk about today is about the interactability and multi-agent systems, and which is very important because we see that in intelligent transportation system basically is all about the multi-agent systems. And what's the motivation behind this multi-agent systems? In many cases, that single agent cannot maybe have enough power or capability to basically be successful. But even with one agent, it's interact with other agents and multiple agents. And the other problem is that the scalability when we have a large number of the agents, and also how they can communicate among the collaborative agents. And our approach is basically we start with some work from actually my PhD that we share the data in a distributed fashion. So basically the idea is that how we can collaboratively do some tasks. So and of course we are interested in to have a communication. So not just agents working separately, for example, connected vehicle on the top or in the robot soccer team, all this interaction and communication matters. So we are working on the robust communication between different agents to learn the different framework, for example, carrying the object. So one of the focus of actually my previous work is on the transportation of, it could be for the construction, for example, here, or for even in the search and rescue domain, how we can basically use the multiple agent to improve the efficiency. So the idea is actually using the real robotic system. Our robot is very simple, very limited. They only have 8 infrared sensors. So, and they only have also one radio antenna. And it's kind of, we consider this robotic system and they communicate with each other for carrying the big object. That the idea is actually basically using this for the search and rescue, for helping the human in the areas that human cannot have access or no GPS or Wi-Fi. And basically by using very limited communication, still they can have basically a connection. And that's important because you see that even in the cities that basically in the tunnel underground or like even under some bridges, your connection is disconnected. So if you just use GPS, maybe is not enough. So having some other alternative and more reliable communication and make sure that you have some redundancy, it's helpful. So that's why we use just very simple and limited sensing, which is just infrared sensors for communication and sharing the information. So this communication provide us the 3 different values: the distance between the 2 robots and the orientation of the robot respect to each other. So you see that here. So we have 2 robots with 2 different orientation, and they can figure out and calculate these numbers, and basically they can measure and send this information. And the result is interesting. So we actually run this algorithm in the domain. You see that with the robot with very limited sensing, no GPS or Wi-Fi, they just communicate locally and just pairwise communication. And you see that how they this is kind of mimicking the person body, how we can carry this body and go out of this space, but just the communication and also collaboration between all this robotic system. And the idea is basically having this model basically having all these basically model for different applications, for example, not search and rescue, also the connected vehicles and other areas that we can share the very limited amount of the data, but still we can be powerful and also efficient. And we have actually 3 parts. So first, the area is explored by the robots, then some of the robots attach it to the object. They do sharing the information to understand the size of the object, then do the perception basically, and then the path planning. So we have the robot as a guide robot, as you see in the video, that basically as a guide robot, as a blue dot, and then blue circle around it. And then as soon as the robot reach basically the person or the robot, the carrier robots reach that robot gets idle, and then just the rest of the path is still there to guide the transporter robot to follow this path. So actually the robots create that path. We also work on the in terms of the learning side of it, so how we can use reinforcement learning for multi-agent systems. Basically, the areas basically is more for the kind of robot and human interaction. We start with the 2 robots to try to, for example, one of them the one on the right side tried to protect the virtual ball. The other one is try to hit the ball. So basically we try to see that how this interaction, we can use some reinforcement learning and decision making to make it happen. So, and the idea is basically we start with simulation and we need to address the challenges in the simulation to the real world, which is in many cases we have to first simulate in the environment and then transfer it to the real world. And this is the result that we run it actually from University of Washington when I was working there. So basically, we had the person player that plays with the robot, and this ball here basically is virtual, and but at the beginning the person is learned from it. It learns basically where that the virtual position is, and the person tried to hit it, but the robot tried to protect it. So basically, the whole idea is how we can model this human-robot interaction, which is very important in different applications, including the smart city and transportation system. So, and actually, interestingly, that robot continue to learn over the time, and also, but sometimes that human also plays very well, and you see different actually scores. For example, of course, higher is better, and sometimes robot, this is negative, is kind of the robot beats the human, but it's possible that the two possibilities, for example, just running this video for a little bit, and you see that this human this player tries a little bit distract the robot and kind of the robot, but still so plays better than the robot. So it's kind of the 70% now, the human plays. So actually I just move on to the last one. She's kind of very dynamic and moving around. So basically make it that robot kind of thinks that the ball is the person is different places kind of, and it gets the highest score. So it's kind of, you see that all different possibility based on the human being, and also this is one of our work that we measure different factors and how actually the person actually in different plays and how it actually affects based on their behaviors, based on their even some vital behavior, like for example vital values or signals, for example the heartbeat, on if they play for example for 5 minutes they get tired and maybe they play worse, something like that. Kind of be considered different parameters and different basically outcome of this playing. So I think yeah, so now actually I think this is yeah, I'm going to talk about actually conclude the first part of I might talk about that actually what is left here and how actually we start working on it in our research lab now. So far we talk about transferability, adaptability, and communication basically, and multi-agent systems, that we show that basically how we can bring the robot and artificial intelligence in the real world scenarios. And basically, but there are still many questions unsolved and many other problems that we are interested in. One of them is that it's still artificial intelligence in many cases is still not very cheap. So for example, sensors are all, most of the efficient sensors are still very expensive. So if you want to use, for example, LiDAR for all the cars, maybe it costs a lot for the cars. And also, of course, the safety and resiliency, especially when we have the human and robot interaction, you see that actually we don't get the similar result. For example, in the interaction with the human for the playing with the robot. And of course, the scalability, we show that maybe a few numbers of the connectivity, but in general, that how we can, if you want to have it, for example, running this system for the whole city, for maybe 1,000 car, even like how we can actually extend it to a scalable number of the agents. And of course, adaptability in different domains matters. So and the privacy issue, other things that, for example, if you want to share the data with others, just the data, maybe the privacy be a problem if you want to use the other data for your experience. Basically, this is the first part I want to talk about a little bit about the low-cost autonomous navigation, basically. So how we can reduce the cost. One of them is, of course, is just the sensors is one of the more expensive part of the basically the self-driving scenarios. And the idea is that how we can reduce the, for example, 3D LiDAR with the cheaper sensing, the camera or radar now. For example, this is the video showing that
This video shows a
one of our work basically that we have actually LiDAR and the camera, 3 cameras for avoiding the pedestrian, and basically this car is moving around, and even like we have a 2D LiDAR. So the idea is that one of them, for example, would be 2D LiDAR is much cheaper to the 3D LiDAR. So we show that, for example, with the combination of this cheaper sensors, but having the more efficient algorithm and fusing between the sensors, we can basically still have a efficient algorithm. So the other one actually basically is just using the camera. So we have this type of the component, all the component of the any autonomous navigation, not necessarily the self-driving cars. And we have the perception, planning, and control side. And the idea is that how we can use all these 3 parts just using the cameras for the part of the sensing. And so just basing the vision. So one of the actually areas that we are working in our lab is basically everything based on the vision and the cameras. And recently we use actually cheap version of the radar and combine it with the light with the camera to have more efficiency. The last part of my talk is about the connected vehicles as part of infrastructure that we have been using now. And in terms of the connected vehicles, the idea that I talk about it earlier today is about using how we can actually combine and fuse the models incrementally. And we actually extend that work by considering combining all the models at the same time. So assume that we have, for example, 3 cars, and each of them has different experience, and they already maybe collect some data from pedestrian, for example, intersections, at intersections, but they are not going to share this data, which is the privacy issue. So just each itself, they learn their own model, okay? And they learn their model, and only instead just they share their model, which is, of course, doesn't have information about the pedestrian trajectories, at least not directly. And then we combine just this all model together. So kind of if you have these 3 cars and they communicate, and we have the connected vehicles, and basically they learn from others' experience. And then we also, of course, we're working on the communication base of this approach. The other thing is basically that for the first one at OU, that we built actually 1 ton scale of smart city. And this city, actually, the idea is that basically to provide and testing environment for self-driving scenarios, as well as a smart intersection. You see that in this picture and the video that there is the LiDAR, 3D LiDAR on the top. And instead of each car having the LiDAR, they only have the cameras, but they can communicate, and just the cheap 2D LiDAR, but they communicate with this computer connected this smart intersections, and basically they can avoid each other basically at intersections. So, and basically intersection or the smart infrastructure here share some information regarding the position of the other cars, and share with others, with the cars neighboring by, and the car make a decision to be safe. Basically there are 2 ways that we consider that. One of them is that the intersection also shared decision. So a smart intersection also share the decision, and the car just follow that. But usually we consider that this control to the car, so the car just get the warning that, for example, there is another car is coming, and they basically make a decision to avoid any crashes. And this is the environment that we do it for. Our idea is basically that actually transfer this mini city to another environment. Now it's actually in the basement of the RPF in the engineering building facilities, but we are looking for actually the permanent space, and basically having some area with a high ceiling. We can also fly our drones. So we have the combination of the cars and basically the drones for different strategies, including emergency response management by having this heterogeneous multi-agent system, basically, and also doing work on the advanced air mobility. So, so basically, this is the whole idea about the mini city that we have so far, and we are working on that to expand it. And just very quick about the lab that we have, actually, how we can actually pursue this approach is basically to focus on all this topic that I talk about it here today is autonomous navigation, advanced air mobility, basically, and also multimodal localization mapping. That's the other area that I didn't talk about today, but is a part of our lab focus. And so far we have software, hardware and software set up. So we have both educational purpose robot like a JetBot that we got, that we use it for the courses, the AI course that I'm teaching this semester. And also we have other robots, a race car that basically is 1/10 scale race car that they are equipped with cameras and 2D LiDAR and high computing processors. And we also have the drone that it's a hexacopter, so 6 propellers with processors. And actually, basically, we are adding more sensors now. They only have the cameras for now. And basically, this is the video from the mini city. We actually expanded a new version of it. So you see on the top, you use some AI generated basically background for this mini city for improving the algorithm for the visual based basically mapping side. So we already done some experiments here. So, and the idea is working on that intersection and different scenarios, even adding pedestrian or some shape kind of some pedestrian robotic system to also we do it basically some testing basically for evaluation and comparison of the robot behavior with the human driven cars. So yeah, so that's all about my talk. So thanks for your attention. We're happy to get any question. Thank you.
Does anybody have any questions for Dr. Habibi if they want to ask a few things? Dr. Sun, did you have anything for Dr. Habibi?
I have a comment. Gulnaz, I was absolutely fascinated at seeing that sword fight between the robot and the human being. That was absolutely gorgeous. And I just want you to know that I thoroughly enjoyed that video.
Oh, thank you. Yeah, I have a paper. We have 2 papers out of it. I can share that papers if you're interested in. Yeah, actually, that card of work actually is featured in one of the IEEE Spectrum. So I think one of our work that I really like it. That
just to think how the robot has to see, the robot has to think, and the robot has to reply. And you've got that robot doing all those things. That is absolutely amazing. It is reproducing a human motion and try to protect itself. So I think it's an absolutely fascinating problem.
Thank you for the feedback.
Anybody else? Comments, observations on this absolutely fascinating talk that Gulnaz has given us? Go ahead. Roshan?
I mean, makes me think I wish I had taken computer sciences more seriously than what opportunities I had. It's very interesting. At least the autonomous vehicle and the decision-making part of the system is very interesting to see. Hopefully there is, I mean, later, probably once I understand my area of research better, there could be a collaboration where we do some or sort of an automation of our system and figure out how we can develop new strategies to, because I work with novel materials, and so understanding properties of novel materials is important. Maybe some of the data that we have collected could be used to probably predict some things, even if we don't know them.
Yeah, actually, there
Just
are interesting. Now there's some interesting open areas and open research that exactly you mentioned now, kind of using both the human, the robotics, and AI in human in the loop. So for the discovery and material discovery and
Right.
characterization. So I think there are many still open questions that national labs are working on that, and of course, university. So very interesting. Yeah.
Perfect. Perfect.
I have a question, maybe a
Sure.
simple question. The dynamics, I mean, the neural networks that you use for your dynamics, I mean, they all are, I mean, they mostly they are online neural networks, correct? Or you use some recorded data?
Some of them, yes, some of them is no. For example, the one that I started with the certification and verified the robustness and measure the robustness. That one we assume that we already have the models trained on. So basically we collect some data from the drone and then basically or quadrotor and basically we based on the data that we got, we simulate or kind of approximate some nonlinear, for example, MPC. And we use that as our basically control, not the neural network controller. Instead of we replace the classic MPC with the neural network model. And then we see that if our, for example, input of our controller has some uncertainty, not just one deterministic value, how it affects in the behavior of the controller. But other topics that I talk about, like pedestrian motion primitives, it's actually our contribution is to having the incremental learning or continual learning and make it online learning, basically.
Okay, yeah. For some tasks, we need to implement our neural network online. For example, for some based on the environment, for some navigations or for some tracking. For those online, I mean, implementations, your controller, I mean, your control system is infinite time controller. Is it true? I mean, infinite time means the weights are tuned during the, I mean, for example, 20 seconds, 30 seconds online. That means I mean, it means the integration is from the initial time T0 to infinity. That infinity can be, for example, 30 second or 40 second. That means the infinite time controller. But what about if our controller, our algorithm is finite time? For example, like differential dynamic programming that implements, for example, in just 1 second. How those weights can be tuned in such short time?
So okay, there are two ways actually. I mean, this one that I talk about is more on the perception side, by the way. So the one that I showed for the online learning, maybe it's not expanded to the basically the control side of it, because we have different module, and the one that I talk about, the online learning, is more on the perception side, just for the prediction side, not the control side. Okay. But for the control side, is on top of my head, one of them is basically, it depends on how fast your, processors or your algorithm would be, but sometimes, you can kind of simulate it. I mean, forward simulation basically. And then even it's like, you are not executing, maybe it's similar to MPC that, but you don't execute all these basically time finite, but you basically you expect that or simulate it, that's kind of the tree or explore it, for example, using some Monte Carlo search and this type of thing. So maybe that's would be one solution, but I didn't exactly consider that part of the problem, basically.
Okay, I got it. Thank you very much.
Sure.
I don't have any question. If someone have questions.
Yeah, if someone has any questions, then we can take some. We have some time. If not, then we'll just go into chit chat mode. Okay. I think, Farooq, we could just stop recording and probably just go into chit chat mode.
Okay, so I shall stop recording, and in our usual way, we can continue to chit chat. Oops.